May begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class, and just ask you to give us insight today, help us to understand a little bit more about how to solve systems of differential equations and how to understand them, Lord. In my prayer, Lord Jesus. Amen. So I think I probably should just start with setting the terms and conditions. So like definition, let's say, I'll use V, just to use a different letter. dV dt equals to AV plus F vector is a system of ordinary differential equations, ODEs, in matrix, standard, or I think it's standard is what I say, maybe normal, matrix standard form, with a coefficient matrix, A, and here I'm assuming A is like an element of R n by n. All right, so it's an n by n matrix of numbers, and inhomogeneous term F. All right, so what's the usual language applies here, right? So like if F is equal to 0 for all time, then let me call it star is homogeneous. All right. So our goal in this story arc of the course is to learn how to solve this differential equation for like pretty much arbitrary matrices. All right. Now, first of all, I need to explain to you, why I'm going to explain to you why this is like very general. It covers pretty much all contingencies that you might think of. And so I want to show you that, but I also want to just briefly go through the theory here. The theory is not much. Here's the theorem. Well, I guess I still need a definition. R is solution to star if what? You need what? dr dt equals to what? AR plus F, all right? In other words, nothing surprising here, right? It's a solution if when you plug it in it works, right? R is, let's say R sub H is a homogeneous solution to star if dr dt is equal to what? Just AR, all right? Notice that I've dropped off the F, all right? A fundamental solution set for star is a set of n linearly independent homogeneous solutions. Let's say R1, R2, Rn. So a fundamental solution set is a set of n linearly independent homogeneous solutions. A fundamental matrix for star is a matrix of functions, and not just any matrix. It's and let me put a qualifier here, n by n matrix of functions. Say I usually use big X for it. So like R1, R2, dot, 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 Rn, where drj dt is equal to arj for all j. In other words, what I'm writing down at the moment is a fundamental solution matrix is a matrix where every column in the matrix is a homogeneous solution, all right? But it's more than just that. We also want to insist that the matrix is invertible, so where the determinant of x is not equal to 0. All right? So these are just some terms we like to use in here, all right? And so the theorem is given, given star, number 1, there exists a fundamental solution set. Number 2, there exists a fundamental solution matrix. I mean, that's kind of dumb, right? If you've got a set of fundamental solutions, of course you can glue them together and get a fundamental solution matrix. All right? Let me call that matrix X. 3, any solution to dv dt equals to AV may be written as V equals to X times a constant vector. Now, explicitly, what that looks like here, all right, is like, R1, R2, Rn times the constant vector, let's see, C1, C2, Cn, all right? And when we work that out, what we've got is C1R1 plus C2R2 plus dot, 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 plus CnRn. So any homogeneous problem can be written, the solution to it can be written as a linear combination of the n fundamental solutions, and like number 4, are you guys done on the blue? Am I okay to erase that? Yes, no, maybe so? Yes. All right. For if V sub p solve star, in other words, dvp dt is equal to avp plus f vector, then any solution to star has form V is equal to, C1R1 plus da 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 plus CnRn plus V sub p. In other words, it's the sum of the homogeneous solution and the non-homogeneous solution, right? So, what's the problem for us then? The problem, of course, is then to find the homogeneous solutions to these problems, right? And once we have that done, then we'll circle back and we will address the question of how to find non-homogeneous solutions. But that's a much smaller part of the story here. Actually, the problem of finding the homogeneous solutions is really the thing that will dominate our time. Finding the particular solution is kind of an afterthought for us in this part of the material. Okay, so first of all, so that's basically it. That's essentially the theory. This problem has a solution. It exists. We can always find it, actually. And I'm going to show you how in about the next 2 hours of lecture. But before I do that, I need to actually explain to you why this is general. All right, so example 1, here's a linear system of differential equation. Well, here's a linear differential equation, which is not of this type, right? How about this? What if we have a y prime prime plus by prime plus cy equals to 0, right? Well, you guys already know how to solve this, right? But let me show you how to turn it into a system. What we can do is we let x1 equals to y, and we let x2 equals to y prime, all right? Now, y prime is actually what? If I make this substitute, this definition, y prime is what? It's just x1 prime, right? So on the one hand, we have x1 prime equals to x2, right? And how about y prime prime? What's that equal to? Well, it's equal to, minus by prime minus cy divided by a, right? Now we are assuming a is not equal to 0 here, right? So look at that. This gives me then that x2 prime is what? Minus c over a x1 minus b over a x2. All right? And so is that a matrix? So right now, that's not a matrix system yet, but it is 2 first-order differential equations, right? So we can rewrite that as a matrix problem. Let us do that. So this is actually x1, x2 prime. Let's see here, 0, 1, minus c over a minus b over a, x1, x2, right? So this is now I've written it almost in matrix, standard matrix form, normal form. Here's my matrix of coefficients A, right? This I'm saying is like my dr dt, and here's my r, all right? So I can always take a second order differential equation and trade it for 2 first order differential equations. You might say, why would you do that? We already know how to solve those. Don't make it worse, right? But this is something we can do. Now, but we can do more than this, all right? So check this out. What if I had y prime prime minus y equals to 0 and z prime prime plus z prime plus y prime equals to 0. So here we go. These are 2 second order differential equations, right? I want to show you yet again, and let me make them non-homogeneous so it's more exciting. We'll throw a t here and an e to the t over there. All right, that's unpleasant. Can we convert this to a system of first order differential equations? Well, if you understand the idea of the last example, you should be like, well, yeah, we can just do what you did before. We just need more symbols, right? So like, we'll do x1 equals to y, x2 equals to y prime, right? And now we'll throw in an x3 equals to z and a x4 equals to z prime, right? So let's see here. So like y prime prime is you know, y plus t, right? Which is actually what? That's actually x2 prime is equal to x1 plus t. All right? Save that for later. And if I solve that one, I got myself a z prime prime equals to, well, like minus z prime minus y prime plus e to the t, which I can translate into x4 prime equals to what? Like minus x4, y prime was what? That was x2, right? So minus x2 plus e to the t. So save that one. All right. So put it all together. We've got our x1, x2, x3, x4 whoop, whoop, prime equal to some big old 4x4 matrix times the vector of unknown functions, x1, x2, x3, x4, plus a inhomogeneous term. So you guys help me out. What's the matrix look like? x1 prime is what? x1 prime is x2, right? So I do 0, 1, 0, 0 for my first equation, right? Put a 0 over here. Now x2 prime is what? Well, x2 prime is over there. See, it's x1 plus t. So I'm supposed to do 1, 0, 0, 0. That gets me that x1 over there. Right, x2 prime is x1 plus t. So I gotta put a t here. All right, so that's my red circled equation over there. Now the third equation, you can see from just looking at this right here, x4 is z prime, but z prime is x3 prime, isn't it? See that? So that gives me the third row as 0, 0, 1, 0. Right? And there's no inhomogeneous business going on in there. And then finally, my purple equation over there, x4 prime, is what we got? 0 x1s. What's that? 0, negative 1, 0, negative 1. Very good. And my inhomogeneous term is e to the t. All right. So there you go. This is the matrix of the matrix A, and here's your inhomogeneous term F. So yet again, I have shown you we can trade out a system of linear differential equations for a first order system. And I'm not going to prove it to you, but I think it should be clear from these examples that as long as you're given a collection of linear differential equations and systems of linear differential equations, you can always do this reduction of order to convert it to one big old matrix problem, right? So you see, if we can solve the arbitrary matrix problem, we have solved every problem of this type. That's the idea. All right? So how do we solve the problem of this type is the question, right? So I started to show you that last time. And let's circle back to that again, because that argument needs to be repeated. How do we solve the homogeneous problem? The first line of attack is the eigensolution. All right? The first vector of attack is to find the eigensolutions. So I will show you, hopefully, a couple of those today. Now, in your book, if you look, there's another method which I would refer to as, well, ad hoc, the operator method. I just don't even teach it anymore. It gives me no pleasure, and I don't think it's a good method. But there are other methods, all right, besides the matrix method. Basically, the other methods are just like in solving linear equations. We can do what? We can like eliminate, substitute. All those games still exist here, right? If we have time at the end of class, I'll show you an interesting example of that, all right? But so let's get back to the eigensolution. I'll call these eigensolutions. So we were trying to solve dr dt equals to AR for a given n by n matrix. All right. And I said we should guess R equals to e to the lambda t times u, where u not equals to 0 is constant vector. All right. That was my suggestion. And then I pointed out to you guys that in order for that to work, when we plug it in, what happens? So plug in, what do we get? We get d dt of e to the lambda t times u vector is equal to a e to the lambda t times u vector. So we're trying to right now derive necessary conditions on the vector u and the scalar lambda to make it work. Now the calculus here we've already gone through. This is lambda e to the lambda t. U is a constant vector, it just rides along. And then of course over here we got a e to the lambda t u. But the thing about e to the lambda t is it's non-zero, right? So therefore we get that, lambda times the u vector is equal to a times the u vector. But this equation we can trade for the, also a nice equation, a minus lambda times the identity matrix times u is equal to 0. So this right here, this equation, this, if you can find u that solves this, definition, u is eigenvector with eigenvalue lambda for a. If you can find a non-zero vector that solves the boxed equation right there, that makes u an eigenvector with eigenvalue lambda for a. All right? And I explained to you guys last time that having a solution, u is a non-zero solution, right? Does the zero solution work? Sure does. Therefore, must have the determinant of a minus lambda I is equal to 0. So basically this is the so-called characteristic equation of the system, all right? The characteristic equation of the system, the solutions, the roots of the characteristic equation are called eigenvalues. The theory of linear algebra here implies that there always exists at least one non-zero eigenvector for each eigenvalue. However, to be clear, since we're working with real problems, do polynomials always have real solutions? Sadly, no, right? There's also complex roots, right? And so that's going to be a separate talk, right? That's going to be an hour at least of us working out what happens when it's complex. But the answer is pretty much the same. You find the complex eigenvector and you extract real and imaginary solutions in that case. Okay, so hey, let's try this method out on this problem. I won't find the eigenvectors for my example 1, but I do want to find the eigenvalues for example 1. I think it's good to see that. And then I'll do problems without letters in them, but I think it's good for us. It's healthy for us to see what happens here. And it won't take but a minute. So let's set it up. What's the characteristic equation for, this A. All right, so I'm supposed to calculate the determinant of A minus lambda times the identity. So what that looks like is the determinant of minus lambda 1 minus C over A minus lambda minus B over A. Now what I'm doing there, the identity matrix, it's a 2 by 2 matrix. Let me write it out so you guys understand what I'm doing here. It's going to be the same thing every time, so if you didn't get it this time, you'll get it the next time anyway, but let me just be manifest here. So lambda times the identity matrix is specifically, in the 2 by 2 case, lambda times the matrix 1, 0, 0, 1, and so that is lambda 0, 0, lambda. So you see what I'm doing? I'm subtracting this and that. That's coming from this, all right? Okay, so this is a 2 by 2 determinant. It's not bad. So this is like, let me just absorb the minus. I got lambda times lambda plus B over A plus C over A. Or if you like, that's 1 over A times A lambda squared plus B lambda plus C. Well, look at that. Does that look familiar? If I had asked you to guess what was going to happen, you would have guessed this, right? Like, what other polynomial could it be? So you see there has to be some sort of, duplication of the story we already told in this course, where different things happen when this is like a distinct root or a repeated root or a complex root. We expect all that kind of, divergence of storylines to happen here again. All right, let's look at an example with numbers. And we'll just work it out. There is a little bit more in the theory section I haven't covered yet, but I think I'm going to leave it for another day. There's a few cool formulas about the fundamental solution matrix that I haven't shared with you yet, but we'll save it for another day. All right, so basically the order of operations here is for a given problem, we need to step number 1, find the eigenvalues, and then step number 2, find the eigenvectors. And then like step number 3, put it all together, all right? Can I erase? I'm going to erase this business here in a second. I guess I can wait a second. Here's the probable work. Start out 2 by 2. I guess this is example 3. Let's look at the differential equation x prime equals to minus 4x minus y. And y prime equals to 5x plus 2y. All right, let's see if we can find the general real solution to this character here, all right? So what's the first thing we got to do?
Do our x's?
Do our x's. What do you mean by that? I mean...
I'm not like split them up like you did before.
Oh.
With the x1, x2.
Oh, okay, yeah, but well, I see what you're saying, but we don't have to do that. What we can do, that's not a bad idea. I see why you think that, but I wasn't, those other two examples, I wasn't trying to say we always need to use x1 and x2. I was just doing that to like show the pattern there. But here, we could just use x and y for the variables. Just let them be.
Oh, I see.
Just let it be. And so we just need to look at it as a matrix problem, you see? Because once we look at it as a matrix problem, then we can find the eigenvalues. And then we can find the eigenvectors. All right? So let's do that. So the matrix is minus 4, minus 1, 5, 2, xy. All right, there we go. This is the matrix we're looking for. Here's my A. So step number 1, find the eigenvalues for A, all right? So we need to look at the determinant of A minus lambda I, which is the determinant of minus 4 minus lambda, minus 1, 5, and 2 minus lambda. I'll put some dividers in just to make it a little bit easier to digest. I'm going to do a trick I always do here, which is to absorb the minus. So that's really lambda plus 4 times lambda minus 2. I hope you see what I did there. When I multiply the diagonals, right, because I've got a minus on both, instead of writing 3 minuses, I just write 1 minus, and minus minus gives me plus. All right, anyway. Then this is, of course, lambda squared plus 4 minus 2 is plus 2 lambda. I've got minus 8 plus 5 is minus 3. So what we have is lambda plus 3 times lambda minus 1 and factored. Set that equal to 0. So eigenvalues are, let's say, lambda 1 equal to minus 3 and lambda 2 equals to 1. You guys with me? Next step, we need to find the eigenvectors. All right? So we'll do that. So we'll start with the first one. So we're looking for lambda 1 equals to minus 3. So I'm trying to find u1, which I'm going to call it like uv, such that, you know, a, I'll do down here. So I've got, fine, a minus lambda 1I times u1 equals to 0. But what that looks like then is, my lambda 1 was 3, right? So I'm trying to solve a plus 3I times u1, which is what? A plus 3I is, I add 3 to the diagonal, so I've got minus 4 plus 3, which is minus 1, 5, 2 plus 3, 5, times my u1 vector. I'm trying to set that equal to 0. Question. If we did the math right, can these equations be distinct? What would it mean if the rows corresponding to the matrix we're looking at are distinct? Well, that would mean we have different equations, like basically lines with different slopes. They would only intersect at the origin. The unique solution would be the 0 solution. If that was the case, we'd be in trouble because we wouldn't have an eigenvector. We wouldn't have a 0. We'd only have 0 as a solution, right? So if you do this correctly, it must be the case that there is a redundancy between the rows. And you can look at this and you can see that, in fact, this is totally interchangeable with just what, like, you know, minus u minus v equals to 0, right? That is, this one equation is the same as the second equation, which is just 5u plus 5v equals the same equation, right? So, okay, great. So this gives me v is equal to minus u, and then I just choose u equals to 1, therefore u1 equals to 1 minus 1. Now, to be clear, I'm not finding every possible eigenvector right now, all right? I am simply finding a token eigenvector. If you'd like the set of all possible eigenvectors, with eigenvalue minus 3, simply take a scalar multiple of that. Right? Every eigenvector with eigenvalue minus 3 is a scalar multiple of that particular one I wrote there. So next up, lambda 2 equals to 1. All right. We want to find u2, and we're going to reuse this u and v. U and v are disposable variables for me, guys, such that a minus lambda 2I u2 is equal to 0, right? But what is that? That's explicitly a minus the identity matrix times u2, which is, all right, minus 5 minus 1, 5, 2 minus 1 is 1. All right? So now I've got to solve this. All right? So, I mean, you pick your poison. I think I like the second row. So 5u plus v equals to 0. And I'll solve for v again. Minus 5u. I'm going to choose, because I can, u equals to 1. And that gives me u2 is 1 minus 5. And there you go. That's a token eigenvector for eigenvalue 2, namely 1. All right, now I've got my eigenvectors, I got my eigenvalues. Yes, sir?
Do we always choose u equals 1? And if not, what are we choosing?
You can choose anything you like except for one thing. There is one mathematical tree you must not eat from. 0, yes. For if you eat of that tree, you will surely die. Well, you won't die, but I'll take all your points because it shows you haven't studied. But yeah, don't. I mean, I'm telling you this now, but it's going to happen. It's just, I don't know if me telling you this is making it happen. I don't really think so. I think it's just an intrinsic feature of differential equations classes that someone on the next test will give me 0 as an eigenvector. And the reason that will happen is because you found the wrong eigenvalue. If you find the wrong eigenvalue and you go looking for eigenvectors, only the 0 vector will be there for you. Because what that means is you're trying to solve a minus lambda I equal to 0 when that matrix is actually invertible. And if it's invertible, only the 0 solution exists. But that is not what we're looking for. We're looking for eigensolutions because those are the ones that go through this whole song and dance over here. So what's the general solution here? Our solution then is R of t equals to c1 e to the lambda 1t u1 plus c2 e to the lambda 2t u2, right? And explicitly here, we have xy equals to like c1 e to the minus 3t 1 minus 1 plus c2 e to the t 1 minus 5. And that, my friends, is the general vector solution to this problem, which is usually what I ask for. All right? This is the general vector solution to star. Now, what if we wanted to find what would the scalar solutions be? Some professors insist their students find scalar solutions because they feel like they don't understand it if they don't. I'm not that guy. So like literally the solution here is x equals to c1 e to the minus 3t plus c2 e to the t and y equals to I mean, I don't even usually write xy here, guys. I usually just write like r. I'm content to write that, you know? Fine. So I got x. X is that. My y is minus c1 e to the minus 3t. Minus 5c2. So you see how they're all intertwangled? Check that out, right? They're all interlinked. These differential equations are coupled.
So it's solving for both equations at once.
That's right. The eigenvector method solves for both equations at once. Now, you might wonder, how is that happening? What dark magic are you using that makes this all happen? I just guessed this solution, and we worked out the necessary consequences, and we worked it out for this matrix, and lo and behold, there's a solution. But yeah, it does beg the question of what's really at work here, right? Why is this working? And the answer to that question ultimately is that if you take the system and you convert it to eigencoordinates, the system uncouples in eigencoordinates. All right, so basically if you took this system here and you rewrote it in eigencoordinates, it would look like this. It would look like dx bar dt is, minus 3x bar and dy bar dt is equal to y bar, which would immediately give you x bar of t is equal to let's say b1 e to the minus 3t, and you'd immediately integrate and get, not integrate, but separate variables, the usual song and dance. Y bar of t is like b2, e to the t, right? And so if we use eigencoordinates, which I would have to explain some other day. Actually, I probably will not explain that in here. I explained that in Math 221. Not here so much. But it's true. If you change coordinates to eigencoordinates, it uncouples the problem. So just the x bar business is the x bar business, the y bar business is the y bar business. You can solve these separately, and just like that. But we don't have to, the thing is, we don't have to do that, right? It doesn't matter, because we can find the solution simply by finding eigenvectors and piecing things together. All right? So, listen, I have many more examples to show you, but I think in the time that remains, if I can get this thing to work, I want to show you an example that doesn't use the eigenvector method. So this other example I'm going to show you, it's a pretty hard example. It's something I just worked out for my Physics 331 class. So this is a natural system of ODEs, which appears if you're trying to solve the motion of a charged particle in the presence of an electric and a magnetic field. And let me see if I can find it here. I found it. See if I can get it open. Do 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 do. So, as we look at this example here in a second, you'll notice something about this problem. If you try to compare it with the example I just did in class, the method I'm going to use on the one that's on the projector right now, that method would not work for the problem we just solved in class. So this problem is both easier and harder. It's easier in the sense that you don't really need matrix techniques to solve it. It's harder in the sense that it's, it's got a lot going on. So if you have the Lorentz force, right, you've got an electric field and a magnetic field. E plus V cross B times Q gives you the total force. I'm assuming we have a constant electric field this way and a constant magnetic field that way. You work out the cross product of the velocity and the magnetic field, you get this. Since my magnetic field is just in the x direction, you only get non-trivial terms here and here. If we use the dot notation, our V cross B actually just ends up being 0, B V dot minus B Y dot. And my electric field is just in the z direction, so the total force is just this. And of course it has to be equal to the mass times acceleration, which in the double dot notation just looks like so. X double dot x hat, y double dot y hat, z double dot z hat. Which means that I have to solve this system of second order differential equations to find the trajectory of my charge. There's zero acceleration for the x, so that's not even going to appear again in the solution. It just does what it does. And because I'm assuming that the charge is initially at rest at the origin, it just sits in the x equal to 0 plane forever and ever, amen. All right? But interesting stuff happens in the y and z because my double dot is equal to qbz dot, and mz double dot is equal to this. So I rewrite this as y double dot is equal to omega z dot, and z double dot is equal to omega e over b minus y dot. Now here the omega is a so-called cyclotron frequency. It's qb over m. Now, so when you see something like this, this is a gift. This is a gift. There's derivatives everywhere. So you can integrate that thing. So I did that. I integrated that equation, which gave me y dot is omega z plus c1, which then I plug that in over here to give me that, which then gives me, a second order differential equation in z. Well, we own, these are easy, right? Z is, c2 cosine omega plus c3 sine omega plus my particular solution, but this is just a constant. So the particular solution is actually particularly easy to find here. It's just that. And so lo and behold, we get that solution, which in total gives me z. Did I ever move the camera? Oh well. I get this and that. Now I apply my initial conditions, which short of, after a bit of algebra, I find that my solutions are y is equal to that and z is equal to that. Everything's in terms of the cyclotron frequency, and you can see that this is some kind of like circular motion. If you eliminate cosine and sine by using cosine squared plus sine squared, it gives you this equation, which shows you that actually the path travels a circle, but not really. I mean, it's the center of the circle is at r omega t for y and r for z, and it's got radius r, and it's just kind of like this, and right. So if you have a circle that's translating like that if you do that right, it gives you a cycloid. And so this is the motion of a charged particle that's initially at rest, but then subject to crossed electric and magnetic fields like this. But the mathematics you guys are learning is exactly what you need to work this out. All right? But I mean, you see that actually this particular problem, the only thing here that's really intrinsic differential equations would be that y prime prime plus omega squared, where I use the second order constant coefficient solution, right? That was the thing that was very much not just calculus 1 argumentation, But anyway, inevitable. Is this on the test? No, obviously not. I don't expect you guys to have a command of like the Lorentz force and how to like implement it in three-dimensional geometric situations. That would be monstrous for you guys here, right? But if you're electrical engineers, you should be happy about this example, I think. Hey, where'd he go? Anyway, see you guys.